Hello and welcome to another installment of Operating System from Scratch. Before we begin, let's recap what we've achieved so far. By now we've created code we want to run on the bare metal. That code turns on both onboard LEDs. We've managed to compile it for 64-bit ARM, aka AArch64, and extract the raw binary we want to load. If you're unsure of any of those steps, please check out the previous videos on the subject. If we go to the boot ROM page on the Linux Sun Xi site, which is, unfortunately, as close as we've got to getting authoritative resources on the boot process, we'll see it mentioning FEL mode and Egon BRM mode. Can't blame Allwinner for lacking imagination where naming stuff is concerned. Let's start with FEL. We've actually seen that name mentioned before in the disgrace masquerading as a chapter about the BROM in the H616 user manual. FEL is a debug mode, which we enter if no other boot source is found. In other words, all we need to do in order to start it is take out the SD card. FEL uses something called USB on the go or USB OTG. In practice, this fancy name just means we connect the USB-C port of the Orange Pi 02 to a computer. Conveniently, this means the computer also supplies the power to the Pi. Indeed, we can see in dmesg that it detects a USB device connected. Of course, merely connecting does nothing. We need to actually be able to interact with it. Luckily, that's where the Linux Sun Xi community really came through. They've built a set of command line tools for managing various aspects of working with the Allwinner family of chips. I should point out that, to the best of my knowledge, these tools only work on Linux. If you're on other platforms, I'm sorry for you. With the tools compiled, we can run the Sun Xi FEL tool to get a list of commands. First, we'll run the version command. The output shows us that our H616 is correctly detected. That's good. We can now try to manually load our bootloader. The write command copies a file from our computer's file system into the Pi's memory. Conveniently, we already have an image file we want to load, and we even know the address this file should go to. We'll write our FSL image file to address hex 20000. The exe command will tell the FEL to execute our code. Hit enter and nothing. At this point, we're not sure why things didn't work. Either our code did not execute, but why? Or it did, but what we did was not what we were supposed to do in order to get the LEDs to turn on. Running the version command again reveals that we did manage to do something. FEL no longer responds to us. That's easy enough to rectify, but now what? When all is said and done, our program is very simple. It writes hex 77117777 to address 300B04C, and then writes 3000 to address 300B058. Okay, it doesn't sound very simple, but it really is. In fact, this is simple enough that we can ask FEL to do those two operations and see the result. This will allow us to make sure we've at least read the user manual correctly. Write L, the values, and it works. The LEDs came on. So we can now say with certainty that our reading of the user manual is correct. It's our code that didn't run. I typically try to present the problems and solutions one faces in the order one, i.e. you, are likely to face them. I'm trying to teach not only how to build the actual OS, but also how to overcome the problems one might face when trying to do it. Occasionally, the way to find a solution is just too long. This particular problem, how to get the code we compiled to actually run, held me back for several days until I found out what I did wrong. It is not possible to shrink everything I tried and still get a 15 to 20 minutes video. So in this particular case, I'm going to show you the solution first and get around to how I found it myself later on in the video. If you're impatient, skip to the timestamp that appears on screen now. 12 minutes 3 seconds. That wasn't so difficult. I wonder why other tubers never read it aloud. Looking at the command's FEL support, we see reset64. The text next to it is a little cryptic. RMR requests for AArch64 warm boot. What this does is warm boot in AArch64 mode. This gives us a clue as to the problem. We've compiled our code into AArch64, i.e. 64-bit ARM machine language. The CPU starts up in 32-bit mode. Our code doesn't do what we want because it is written in the wrong machine language. So let's try this again. Write the image to address 20000 and issue a reset64 2000. And the lights turn on. Congratulations, you've just ran your first bare metal program on the Orange Pi 02. Of course, this isn't exactly a good way to get our code to run. What we want is to write our program to an SD card and have it just run when the power goes on. If you recall from way back, when this video was still young, at roughly 38 seconds and 19 frames, I've talked about the boot ROM and mentioned the Egon. It is now finally time to expand on what that is. Following the link at the BROM page, we at least get the reason for the descriptive name. Egon is what happens when you view the magic number identifying this as a valid boot. A magic number, for those who are unfamiliar with the concept, is a series of bits, preferably randomly chosen, that allows the code to verify that it is indeed looking at what it thinks it's looking at. In our case, meeting the sequence of numbers that spell Egon tells the Inchi bootloader that you mean this to be the second phase loader, or SPL. Looking at the card layout, we see we need to write an image with the proper magic number to sector 16, that's 8 kilobytes into the SD card. At this point, I should point out that another area of the wiki claims the bootloader should be written to sector 38,192. Luckily, I've only seen this text after I've already succeeded in booting via the first way. Since that is about 16 megabytes into the SD card, I highly doubt this is true. Someday, when I actually have some time, I'll try disassembling the BROM and see if it's true. There is some documentation of the header format in the wiki, but mostly it references a tool called MK-SUNIX-I-Boot for creating it. The page for the tool says that this tool is now integrated into the U-Boot main sources. As we'll see, it's no longer even called that. It is time to get U-Boot, or Das Universal Bootloader. We also need to check out a project called ARM Trusted Firmware. I won't go into too much detail on what the ARM Trusted Firmware is, except to state we don't really need it. Booting through it enables certain CPU modes of operation that mostly matter for running virtual machines. Since that's not in the card for Saros, we're not going to be using it ourselves. We will still compile it, as U-Boot is only kinda working without it. We compile the trusted firmware with a simple make command. We just need to give it the target triplet of the cross-compile toolchain to use. See the previous video if you don't know what a target triplet is. We'll also tell it that our platform is the H616. I won't go into all the details of building U-Boot, as that's totally off topic for what we're actually trying to achieve here. Quickly, U-Boot has default configurations for all supported devices. We give make the Orange Pi 02 defconfig target to tell it to use it. We also need to tell it the target triplet the toolchain uses. Building is done with the same command line minus the defconfig target. We will add v=1 to tell make to tell us the commands it actually runs, and direct the output to a file while also showing it on screen using the t command. As usual, I've placed all relevant links in the description below. I've also posted links to descriptions of the commands I'm using for those of you less familiar with the Linux command line. Tell them to like and subscribe. Also, like, subscribe, and buy me a beer. Whatever. We can use rgrep, recursive grep, to sort out which files contain the Egon magic, and then HD, which stands for hexdump, to find out which contains it in the right format. This leads us to two files that are bootable SPL images. The source root directory contains U-Boot SUNIX-I with spl.bin, which is the SPL image with the trusted platform code. We also have SUNIX-I spl.bin under the SPL directory, which is the same code but without the trusted platform. Take a SD card, or is it an SD card? Erase it completely and write the signed image to the 8 kilobyte offset into the card. Connect it to the Pi, boot, and we see a U-Boot starting in the serial console. Repeat the same with the image from the SPL directory, the one without the trusted platform, and we see it too starts fine. That is good news, as it means we don't need to worry about the trusted platform, at least at this point in time. So let's see what U-boot did to build this file. One way is to open the build log file we created when we built and follow the commands back. If the make file is correctly built, we can also run make clean and then build just the file we're after. When I compiled U-boot, you may have noticed I did not pass make the -j option. Typically, when a big project is compiled, we can speed things up by telling make to perform several actions in parallel. Despite my computer supporting 12 threads, I deliberately did not do so, as doing so would make the build log less readable. In our case, it is not so difficult to find it from the log, as the commands ran in sequence. Searching for spl/sunxi splbin, the name of the output file, we can see it was created using the make image command. Running the command with no arguments gives us a help screen where we see that -t is the image type, -n is the image name, and -d is the image data, a path. We're not sure what that last option means, so we can search where make actually built that file. We don't have to search very far. A couple of lines higher, we see it was copied from spl/uboot/spl nodetb.bin. Next, we search where that file was created. We find it one line up. It was created using the obj-copy command. We can see that U-boot opted to explicitly specify which sections they copy, but their command line is otherwise identical to what we used in the previous video. I've explained in the previous video why I think our way is superior. We now have a game plan. Build the code as before, and then use U-boot's make image to turn it into an SPL image and flash it to the SD card. Except it won't work. Our 32-bit problem still exists. We know that U-boot is also compiled in 64-bit, as that's the toolchain we gave it. Since we know what the problem is, we can just look it up on the internet. However, when I first struggled with getting my code to run, I did not know what the problem was. The way I found out was to ask, what does U-boot do? Understanding the U-boot make file is not an easy task, but I found a neat workaround for finding out the source file I was after. We've seen that obj-copy uses spl/uboot/spl as the source. The file command confirms that this is an ELF file with debug info. Since we're looking for the code that runs at its beginning, I'll just use objdump to disassemble it and show the source code with the -s option. We see that address 20060, we'll get to why that is later, holds the _start symbol. And we see a test x0x0 command with a comment. I've not managed to find a way to ask objdump to actually tell me which file this source comes from. This despite the fact objdump itself obviously knows the answer. With that said, a recursive search for the comment reveals only one file, archsunxi/boot0.h. Since sunxi is the name of the Allwinner's SOCs, that name even makes sense. This code is a bit delicate to follow. Some assembly required. Get it? Get it?
Move along.
Right. Anyways, the first command, test x0x0, serves no useful purpose for our program flow. There is nothing of interest in register x0, and testing it against itself will always yield they are equal anyways. The wisdom of this command is that the same sequence of bytes, EA00001F, is interpreted differently in 32-bit mode. In 32-bit mode, this sequence means branch to hex 84, or jump 84 hexadecimal bytes forward. In other words, we've managed to code a conditional branch, where we'll fall through to the next instruction if we're in 64-bit mode, but jump to a nearby address if we're in 32-bit mode. Genius! The next 64-bit command is branch to reset, or jump to the reset function, where our program begins. The next command is called a sudo opcode. It is directed not at the CPU, but at the assembler itself. It tells it to leave the next 7 C bytes unused. This means the next line we'll write will be, carry the 1, 84 hexadecimal bytes after the TST command. In other words, what we write next is the landing area for the jump in case we're in 32-bit mode. The next commands are coded in machine language, not assembly. This is because they are written in a different machine language than the one we're compiling. They are written in ARM32, not AArch64. The first block of instructions saves the processor state, in case we'll want to return to FEL. This is necessary as U-Boot has a command to run FEL. Since we have no such plans, we can skip it. The second block of instructions is the one actually switching to 64-bit mode. Please note that some of the registers we use here are CPU registers, while others are H.616 registers. First, we set an H.616 register called RVBAR. This holds the address to jump to after warm boot into 64-bit mode. We set it to the beginning of this code, the branch on 32 64-bit mode command. We then set a CPU external register to tell it to boot into 64-bit mode the next time a warm reboot is requested. We use the same register to actually request a warm boot. Now we have to wait until the boot happens. We start a tight loop where we halt the CPU until an interrupt arrives, and when one arrives, we halt it again. This gives the CPU as much time as it needs to perform a warm boot, at which point we'll start at the _start, decide it is in 64-bit mode, and run our code. Neat. With that, all we have to do is copy this sequence into our code, compile and install, and we'll have our LEDs on.
We're out of time.
I don't care. We're finishing it this video. But I'll just move forward. We'll dedicate the next video to cleanups and explanations. Leave comments if there is anything specific you want me to address. Right. First, create a file called boot0.s. Give it the label start. Copy the relevant part of init from U-Boot, so not the part about saving FEL registers. The BVBAR register on the H.616 is the second one. This complex predefinition is just a pointer to _start, so that's what we'll write here. Boom, first file is done. Next we open leds.cpp. Nothing to change on the leds on function, but we promised boot0s a function called reset. Just make it call leds on and then go into an infinite loop. Boom, second file is done. Now the linker script. Remember, we saw U-Boot starts at 20060 rather than 20000. We'll just copy it here and analyze next time. Also, we want to make sure that code compiled from boot0 is always first in the text segment, no matter the order specified on the command line. Boom, third file is done. Assemble boot0.s, compile leds.cpp, link them using the wrong order on purpose, quickly make sure the resulting file is what we intended. _start is the first function. Good. Extract the raw binary, copy the makeImage command line from the U-Boot build log, write it to SD, hook it up to the Pi, turn it on, and the suspense is killing me. Boom, 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 boom. The LEDs turn on.
Good job.
And we didn't even have to go over time.